Okay, let's look at some of the other systems and see if we can understand why certain substituents direct things in certain positions. I'm going to draw it like this so that it looks like a 10-electron pi system to begin with. So what we want to do in this case, because we're not going to draw meaningful resonance structures of the parent system, is we want to attack an electrophile first. And we want to attack that electrophile in the possible positions that it could be attacked, and then compare the stability of the intermediate. So we're going to attack that electrophile and put it in the one position. So we've broken the aromaticity of that ring. And we're going to compare that to attacking the electrophile and putting it on the 2 position. So those are the 2 possible intermediates that you could generate by attacking, right, at the 2 positions. Attacked by carbon 1 and attacked by C2. And now we can start drawing resonance structures. There will in fact be 5 possible resonance structures for each of these systems. Keeping that sp3 hybridized carbon in position. And the faster you can draw the resonance structures, the sooner we can get to actually talking about them. So the key to success here is to draw these things enough times that you just get really good at drawing resonance structures. And if the ring gets bigger, there are just more resonance structures, right? If you have anthracene, so you have 3 rings, now you're going to have even more possible resonance structures that you can draw. Right? So we're moving those bonds around into the various different positions. In this one, it's a little less obvious how you get that structure, right? You can't get that structure from here easily just by moving a single bond. You've got to move both of these, right? You have to move that and that. So I can get to here, or that one on the right, by moving one of these 2 bonds. If I move this one, I get there. If I move this one, I get there. So there are the 5 possible resonance structures for attack in the 1 position, and the 5 possible resonance structures for attack in the 2 position. We know that the 1 position is favored, so this carbocation intermediate, this intermediate must be more stable. This one is the less stable intermediate. They both have the same number of resonance structures at 5, so it can't be the total number of resonance structures. It must be the stability of the different resonance structures. So do you notice something, right? You should have noticed that immediately we attack the electrophile, we've broken the aromaticity in the right-hand ring. The right-hand ring is no longer aromatic because it has an sp3 hybridized carbon in it. What about the left-hand ring? Is the left-hand ring still aromatic in this intermediate here? Yes, right? That's still a cyclic pi system. What about here? Yep, still aromatic. What about here? Nope, now we've broken the aromaticity of the second ring. So these three intermediates do not have either ring having a cyclic pi system. What about the other set down here? This one's still aromatic. But notice that because the positive charge is next to the ring, the very next resonance structure breaks the aromaticity of that second ring. So we have 4 resonance structures here that no longer have an aromatic system, whereas in the top one we have only 3 resonance structures that no longer have an aromatic system. This additional structure that leaves the aromaticity of the left-hand ring, the second ring, intact, is the reason for the greater stability of that set of resonance structures. Right? 2 resonance structures that maintain the aromaticity of the other ring versus 1 resonance structure that maintains the aromaticity of the other ring. You could, if you're trying to determine ahead of time where the positive charge is likely to show up, as soon as you draw that first resonance structure, I think you've noticed that it's every other carbon, right? Every other carbon has a partial positive charge. So as soon as I put that on there and determining that there's going to be positive charge here, I can actually put triangles in the ring like this. And these will be the other places the positive charge will be in the various resonance structure, right? So here, and then up there in the next one, and then down here. Right? Those are the various places that you should be seeing that positive charge, every other atom. Did I draw the same resonance structure twice in this one?
Yes.
Because there should be one that has the positive charge
It's
here.
the second and the fourth one are the same. Those 2 are both the same.
Yeah. So I didn't draw the one that has the positive charge here, which I should have. So it turns out it's a good idea to do this and tell yourself where the positive charge should be so you can make sure you've got all the resonance structures. And for this one, right, similarly, once we attack here, we're going to put the positive charge there, and then we're also going to put it on the other places that you can determine by drawing those triangles in there. So we got it on the 2 bottom carbons here and here, and then we've got it on the 3 upper right ones. So that's a shorthand for determining where the charge should be, and then you can go through and move the electrons around to make it so. So that makes sense. We can explain the attack in the naphthalene in the 1 position by drawing 10 resonance structures and then comparing the stability. Let's apply the same reasoning to the system that has the nitrogen in the ring, quinoline. We know it's going to go to the ring that's not deactivated by the presence of the nitrogen. We know it's going to go into the position that's adjacent to the other ring. And we know now why it wants to go into that position that's adjacent to the ring. This is the ability to maintain the aromaticity in the second ring. Let's do the same thing we did. Let's attack it in the two positions. And then start drawing resonance structures. We can shorthand, right? We know once we've attached it here, by the same argument, we know that our positive charge is going to end up on every other atom. So we know our positive charge is going to end up in exactly the opposite positions, right? Notice that none of these coincide. Positive charge is on 5 different atoms. There's 10 atoms in the ring. If you attack at the one position, it's on these 5 atoms, and if you attack in the two position, it's on these 5. And then we can draw all our resonance structures. Positive charge, not a If you're thinking this is kind of a pain in the ass, you're not wrong. Hopefully I got those 5 right. Did I get them right? Right, so we should have on these 3 atoms, we have that one, and the other 2. Looking good? So we can make the same argument, right? Two aromatic versus 1 aromatic, so it ought to attack there. What about attacking down at the other position? So we attack here instead. Because now those two positions are different. You'll notice that attacking at that 8 position gives the positive charge in exactly the same locations as here attacking in the 6th position. So we can certainly explain why C5 is favored over C6 and by implication over C7, right, because of the extra aromaticity. But we're going to have to come up with a different way of explaining why it likes C5 better than C8. Hopefully I got them right again. You'll notice that this one still has 2 aromatic rings. Attacking in either of those positions adjacent to the other ring allows me to maintain aromaticity in 2 resonance structures. Right? Attack at C5 does, attack at C8 does. This one doesn't. But you'll notice that attack at C6 and attack at C8 both have something that's not good, that's going to destabilize that ring. Can you see what that is? One of those resonance structures is particularly poor for those 2. A whole lot more poor for those 2 than it is for any of the others. And that's this. You've got a positive charge on nitrogen, and you've got a positive charge on a nitrogen, right, that doesn't actually have a filled octet. It's okay to put a positive charge on a nitrogen that does have a filled octet. It's not okay to put a positive charge on a nitrogen that does not have a filled octet. So that's really not good. This one doesn't have that problem. On the other hand, this is closer to the nitrogen than that is. So inductively, this should be less favorable. Right? C8 is more favorable because the electrophile is further away from the nitrogen. So inductively, right, that nitrogen is deactivating C8 less than it's deactivating C5. That makes sense? The closer you are, the more you deactivate it inductively. Right? C8 is further away. The electron withdrawing nitrogen is having less of an effect. So you've got this competition, right? Inductively, C5 is less favorable than C8, but by resonance, C8 is much more favorable because it avoids putting the positive charge on the nitrogen. And because you get that competition, you don't get a great deal of selectivity. You're going to get both attack at C5 and attack at C8. Unfortunately, to really understand the quinoline system, we had to go to 15 freaking resonance structures. Right? I didn't do attack at C7. You'll find that if you do attack at C7, though, you're going to put your positive charge in exactly the same locations as you would for C5, right? Which means you won't actually have the positive charge on nitrogen in any of them, but you also won't have the intact aromatic ring in 2 of the 5 resonance structures. So what's interesting about that, where you've got that competition between the inductive effect and the resonance effect, is if you switch the position of the nitrogen and you draw isoquinoline, where the nitrogen is over here, you actually get a much more selective reaction. Again, you get primarily attack in the ring that didn't have the nitrogen, because the nitrogen is deactivating that ring. If you put that in a mixture of concentrated nitric and sulfuric and nitrate that, you're going to get attack here. Get attack there. But now you're going to get much more of this, like 72%, I think, to like 8%. The yield's not very good for these reactions, but you get much greater selectivity for this position than you did in the case of the quinoline. So why is that? We could draw another 10 resonance structures, 5 for attack here and 5 for attack there. We know that attack in either of these positions adjacent to the ring is going to give me 2 resonance structures that are aromatic, right? Just as it did for naphthalene and quinoline. So instead of doing that, let's draw the shorthand and figure out where the positive charge is going to be. Inductively, which should be more reactive here? This one or the top one? Which one's closer to the nitrogen? So it should be less reactive. So if the inductive effect were the only thing in play, we would expect this to be the major problem. But what about resonance? Where's the positive charge going to be if I attack here? Right? It's going to be in those locations. Versus if I attack here, where's that positive charge going to be? So I don't actually have to draw the resonance structures. To determine that that is less favorable by resonance as well. By moving that, right, by moving that nitrogen, I've caused the attack at the position closer to the nitrogen to not only be less favorable by resonance, but also to be the one that puts the positive charge on the nitrogen in one of its resonance structures, an unfilled octet on nitrogen. So now both the resonance effect and the inductive effect are saying that this should be more favorable. Obviously, we get better selectivity when the resonance effect and the inductive effect agree than when they don't agree. So isoquinoline can be reacted, electrophilic aromatic substitution, to get a much more selective product. The same thing that we've been talking about here, the lack of desire of putting the positive charge on the nitrogen, is going to explain why pyridine likes to get attacked in the 3 position. Because if I attack pyridine in the 3 position, I never put the positive charge on nitrogen. Whereas if I attack pyridine in the 2 position or the 4 position, then the positive charge has to be on the nitrogen. Only attacking the 3 position keeps that positive charge off the nitrogen in all the resonance forms, so the 3 position is the position of attack. For the 5-membered rings, the difference between attack here and attack in the other position is actually in the number of resonance structures you can draw. If you attack here, you actually have the ability to draw a 3rd resonance structure by pushing that pair of electrons to nitrogen. The nitrogen is okay with having a positive charge on it if it's also got a filled octet, and in that case it does have a filled octet. If you attack in the 3 position for the 5-membered ring, put the positive charge there, you can put a resonance structure that has the positive charge on nitrogen. But because nitrogen can't expand the octet, you can't move that pair of electrons over there. There's no 3rd resonance structure possible. 3 resonance structures is better than 2 resonance structures, and attack in the 2 position allows you to delocalize that charge onto more different atoms. Right? So 2 resonance structures that have a positive charge on carbon and 1 that has it on nitrogen, here you just get 1. And there's no way to put the positive charge into that other side of the ring. So more resonance structures is better. More resonance structures that maintain aromaticity in at least 1 ring is better. And resonance structures that keep the positive charge off the electronegative element when the electronegative element has an unfilled octet are also critical. Those are the arguments we're going to make for determining where things react.